Hi guys, I will explain tire slips and the sign convention from longitudinal slip to lateral slip. Here I have a quiz for you. Which of the following correctly describes the sign of the slip speed? Negative in braking, positive in braking, negative in both braking and traction, positive in both braking and traction. Let's review the practical slip. Two important speeds for calculating the practical slip are the wheel center speed Vx and the linear speed of rolling Vr. Vx is the speed at which the wheel center actually moves along the horizontal x-axis, and Vr is the linear speed of rolling. The practical slip is defined as in the equation 1 based on the wheel center speed Vx. Furthermore, the value obtained by subtracting the linear speed of rolling Vr from the wheel center speed Vx is the slip speed Vsx, and the practical slip can be expressed as equation 2 using slip speed Vsx. A theoretical slip is defined as shown in the equation 4, based on the linear speed of rolling Vr. Alternatively, it can be expressed as in the equation 5 using the slip speed Vsx. During braking, the slip speed is positive, and therefore the theoretical slip is negative. During traction, the slip speed is negative, therefore the theoretical slip is positive. Let's find out the relationship between the theoretical slip and the practical slip. The theoretical slip can be expressed as a function of the practical slip. Among the 6 equations, from equation 1 to equation 6 obtained above, equation 7 can be obtained by substituting Vr of equation 6 into equation 5, and the equation 8 can be obtained by dividing the denominator and the numerator of equation 7 by Vx respectively, as shown in the equation 8. The theoretical slip kappa t can be expressed as a function of practical slip kappa p. A global slip occurs when the linear speed of rolling and the wheel center speed differ from each other. When the free rolling tire receives braking or traction force, global slip is a physical quantity generated by the entire tire, not just one point of tire. During traction, the road surface drags the wheel center, so the wheel center speed relative to the road surface occurs in the negative direction of x-axis. During braking, wheel center drags the road surface, so the wheel center speed occurs in the positive x direction. It should be noted again here that the slip speed Vsx is defined as the value obtained by subtracting the linear speed of rolling Vr from the wheel center speed Vx. So it has a negative value during traction and a positive one during braking. Therefore, the practical slip and the theoretical slip are positive during traction and negative during braking. Let's consider the slip distance for infinitesimal time. During traction, the road surface drags the wheel center. So the displacement of the tire contact patch relative to the wheel center occurs in the positive x direction. During braking, since the wheel center directs the road surface, the displacement of tire contact patch occurs in the negative x direction. The slip distance dsx is positive when traction, negative when braking. Therefore, longitudinal slip kappa can be expressed as in the equation 9. It is positive during traction and negative during braking. Now let's review the slip speed. At braking, the speed of the wheel center O is faster than the speed of contact patch center C, and the difference between the two is the slip speed Vsx. Therefore, slip speed during braking is positive. Conversely, when traction occurs, the speed of the wheel center O is slower than the speed of contact patch center C. Therefore, the slip speed during traction is negative. Therefore, practical slip kappa can be expressed as in the equation 9 and has the positive value during traction and a negative value during braking. Let's review how to calculate the practical slip from the effective rolling radius. Assuming that the instantaneous angular velocity is constant at omega f during braking or traction, and the effective rolling radius Re on changes, the vertical slip kappa p can be calculated using the free rolling radius Rf and the effective rolling radius Re during traction or braking as shown in the equation 10. As shown in the figure, the wheel center speed during braking is greater than the omega f Rf over the linear speed of rolling. Since the instantaneous angular velocity omega f is assumed to be constant, Re must be greater than Rf. Therefore, the effective rolling radius Re at braking becomes larger than the free rolling radius Rf. During traction, as shown in the figure, the wheel center speed is smaller than omega f Rf over the linear speed of rolling. Since the instantaneous angular velocity omega f is assumed to be constant, Re must be smaller than Rf. Therefore, during traction, the effective rolling radius Re becomes smaller than free rolling radius Rf. Braking and traction are represented together as shown here. The red solid line represents the pre-rolling. During braking, the effective rolling radius increases as a blue dotted line, and when traction, the effective rolling radius decreases as a blue dotted line. Therefore, longitudinal slip kappa can be expressed as in the equation 10 and has a positive value during traction and a negative value during braking. At this time, let's review how to find the practical slip with angular velocity. Assuming that the radius Rf is constant during braking or traction and the instantaneous angular velocity omega r changes, the practical slip kappa p can be calculated by using the pre-rolling angular velocity omega f and the linear angular velocity omega r during traction or braking, as shown in the equation 11. Since Rf omega r of the linear speed of rolling Vr during braking is less than Rf omega f of the wheel center speed Vx, omega r during braking is smaller than omega f. In addition, since Rf omega r during traction is greater than Rf omega f, omega r during traction is greater than omega f. Therefore, longitudinal slip kappa can be expressed as in the equation 11 and has a positive value during traction and negative value during braking. From now on, let's review the local slip. Local slip refers to the slip of a point on tire contact patch, not the entire tire. Figured here is the bristle model described in the last video, E54, where Vsx is the local slip speed and the Ux is the local slip displacement. Although the viewpoint is different, the meaning and the expressions of local slip are the same as those of global slip. The practical slip during pure braking can be expressed as shown in this figure. During braking, since the slip displacement Ux itself is negative, the slip speed Vsx is positive. Therefore, the practical slip kappa p during braking has a negative value. The practical slip can be expressed as equation 9 on the base of wheel center speed Vx. When the wheels are locked due to the extreme braking, it can be seen from the equation 9 that Vr is 0 and Vx has a non-zero value. So the practical slip is -1. The theoretical slip during pure braking can be expressed as the same as the practical slip as shown in this figure. During braking, since the slip displacement Ux itself is negative, the slip speed is positive. Therefore, the theoretical slip kappa t is negative during braking. The theoretical slip can be expressed as equation 12 on the base of linear speed of rolling Vr. When the wheel is locked by extreme braking, it can be seen from the equation 12 that the Vr is a 0 and the Vsx has a positive value. So, the practical slip is -infinity. The practical slip during pure traction can be expressed as shown in this figure. During traction, since the slip displacement Ux itself is positive, the slip speed Vsx is negative. Therefore, the practical slip kappa p during traction has a positive value. The practical slip can be expressed as equation 9 on the base of wheel center speed Vx. When the wheel is idling due to excessive traction, it can be seen from the equation 9 that since Vsx itself has minus value and Vx is 0, the practical slip becomes +infinity. The theoretical slip during pure traction can be expressed as the same as the practical slip as shown in this figure. During traction, since the slip displacement ux itself is positive, the slip speed vs is negative. Therefore, the theoretical slip kappa t is positive during traction. The theoretical slip can be expressed as equation 12 on the base of linear speed of rolling Vr. When the wheel is idling due to excessive traction, it can be seen from the equation 12 that since Vsx itself has minus value and Vr has the same amount of positive value as that of Vsx, therefore the practical slip becomes 1. The table here summarizes the signs of variables. The slip speed Vsx is defined as the wheel center speed Vx minus the linear speed of rolling Vr. Thus, the slip speed is positive in braking and negative in traction, and the slip displacement ux conversely is negative in braking and positive in traction. Under normal driving conditions, the practical slip and the theoretical slip are all positive in traction and negative in braking. And in extreme conditions, accompanied by the tire slip, theoretical slip is minus infinity during braking and 1 during traction. Practical slip is minus 1 during braking and plus infinity during traction. Let's review the side slip. In the last video, E56 of combined slip, we defined the steering angle and the side slip angle in the left-handed coordinate to make the side slip and lateral force have the same sign, because it is consistent to derive the related equation, and the rest are defined in the right-handed coordinate. Let's look at braking in a right turn. The practical slip kappa p of braking is negative, and since the steering angle of a right turn is negative according to the left-handed coordinate, the side slip angle has a positive value opposite to that. A braking force Fx is negative and the lateral force Fy is positive when turning right. The self-aligning moment Mz is negative, opposite to the sign of side slip. Because the right-handed coordinate system is used for the self-aligning moment Mz, and since the slip speed is in the opposite direction to the corresponding force, the longitudinal slip speed Vsx is positive and the lateral slip speed Vsy is negative. This time, let's look at traction in a right turn. The practical slip of traction kappa p is positive, and since according to the left-handed coordinate system, the steering angle of a right turn is negative. Consequently, the side slip has a positive value opposite to that. The traction force Fx is positive, and the lateral force Fy is also positive when turning right. The self-aligning moment Mz is negative, opposite to the sign of side slip, because the right-handed coordinate system is used for self-aligning moment mz. And since the slip speed is in the opposite direction to the corresponding force, the longitudinal slip speed Vsx is minus, and the lateral slip speed Vsy is also minus. Let's look at braking in a left turn. The practical slip kappa p of braking is negative, and since the steering angle of left turn is positive according to the left-handed coordinate system, the slip angle has a negative value opposite to that. A braking force Fx is negative, and the lateral force Fy is also negative when turning left. The self-aligning moment mz is positive, opposite to the sign of side slip, because the right-handed coordinate system is used for self-aligning moment mz, and since the slip speed is in the opposite direction to the corresponding force, the longitudinal slip speed Vsx is positive, and the lateral slip speed Vsy is also positive. This time, let's look at traction in a left turn. The practical slip of traction, kappa p, is positive, and according to the left-handed coordinate system, steering angle of right turn is positive. The side slip has a negative value opposite to that. The traction force Fx is positive, and the lateral force Fy is negative when turning left. The self-aligning moment mz is positive, opposite to the sign of side slip, because the right-handed coordinate system is used for self-aligning moment mz, and since the slip speed is in the opposite direction to the corresponding force, the longitudinal slip speed Vsx is negative, and the lateral slip speed Vsy is positive. Let's find the answer to the quiz. Which of the following correctly describes the sign of the slip speed? The answer is number 2, positive in braking. Here we have a summary. For longitudinal slip is defined as wheel center speed Vx and the linear speed of rolling Vr. The theoretical slip can be expressed as a function of the practical slip, and the practical slip can be expressed as a function of the theoretical slip. Slip speed has a positive sign in braking and a negative sign in traction. Slip displacement, on the other hand, is negative in braking and positive in traction. At the normal driving condition, practical and theoretical slips have a negative in braking and positive at traction. At extreme conditions with tire slip, theoretical slip is minus infinity in braking, 1 in traction. Practical slip is minus 1 in braking and plus infinity in traction. For lateral slip, if the steering angle and the slip angle are defined in the left-handed coordinate system and the rest in the right-handed coordinate system, the related equations can be derived so that the slip and the lateral force have the same sign. If you watch the previous videos, you can easily understand the upcoming videos. In the previous video, E57, I explained the definitions of slip in various ways to the question, why the instantaneous center becomes larger in braking and smaller in traction. And on top of those, I explained how the velocity vector appears. Recently, in the video number H58, I explained how the relationship between rolling resistance, longitudinal slip, and the fuel efficiency is induced in a theoretical formula and their meaning on the graphical representation. In the next video, I will explain the principle of high-performance driving. Please hit the thumbs up and catch the brand new videos by free subscription. So, what are you waiting for? See you in next video. Goodbye, guys.